1 teaspoon of a neutron star would be about the same weight as Mount Everest.
In this video, I got the chance to talk to Dr. Andrew Cameron about pulsars and neutron stars. Dr. Andrew Cameron completed his PhD at the Max Planck Institute and is now working at the Swinburne University of Technology studying pulsars and general relativity. Now you might be thinking, what is a pulsar? Well, that's what Dr. Cameron will answer in today's video. Thank you so much for joining us, Andrew. The first question which most people will ask is, what are pulsars?
Well, that's a really good place to start. I've actually got some slides prepared that might be a little useful illustrative aid, if that's okay. So what is a pulsar is an excellent place to start. The short answer is essentially a pulsar is a rapidly rotating, highly magnetized neutron star. Now, of course, that just pushes it back one step a little bit as to what is a neutron star. A neutron star is one of the things that can be left over when a star at the end of its life explodes in a supernova. They typically weigh about 1.5 to 2 times the mass of our entire sun, but all of that material is packed into a ball only about 20 kilometers wide, the size of a small city. So they are incredibly dense objects. In fact, they are the densest objects in the universe, second only to black holes. I think the usual statistic is that 1 teaspoon of a neutron star would be about the same weight as Mount Everest. So they are incredibly dense.
Wow.
So you can see on the diagram on the right, what a model of one looks like in terms of a pulsar. You've got the neutron star there as that blue ball in the center. It's surrounded by a reasonably strong magnetic field. We're talking on the order of 10 million times stronger than the Earth's magnetic field. And then you've got these 2 axes that are marked on the diagram as well. You've got the red one, which is the rotational axis. That's the one that the pulsar is spinning around. And then you've got the blue axis showing where the magnetic north and south pole is. And from those poles, you get these beams of electromagnetic radiation, typically at radio wavelengths. And so as the whole thing spins around, now you get what's shown on the left-hand side in that animation, this effect like a cosmic lighthouse, where those beams are spinning around through space. And if they happen to point in the direction of the Earth, we can see it as a regular radio pulsation, one after the other.
That's super fascinating. One question which I have is that, our sun is made up of protons, neutrons, electrons, which make atoms. So how do those protons and electrons, where do they go? Because, as you said, one of the neutron stars are the end product of a star that dies in a supernova. So where do those protons and electrons go?
So the basic idea is that, the neutron star is the result of a supernova explosion where a star at the end of its life has fused heavier and heavier and heavier elements until eventually you get to an iron core. And the problem with iron is that unlike lighter elements where you put some energy in, the elements fuse together, you get more energy out the other end. Once you've got it to a core that contains iron, that fusion process, the energy balance tips over. So iron won't fuse anymore. It requires more energy in than you get out. When that happens, the core of the star starts to collapse under its own weight. There's no fusion pressure. There's no energy pressure being produced by the interior to hold the whole thing up. Once it starts to collapse under its own weight, you run into a couple of boundaries. The first one is known as electron degeneracy, where you've basically got the atoms packed as tightly together as they possibly can be with each other, and that produces some certain maximum amount of repulsive force. But because your core by now is so heavy, because your star has been massive enough to get to the iron to the iron production stage, that core is so dense and so heavy that the electron degeneracy repulsion force can't support the gravity of that massive core. The process itself is more complicated than I'm going to get into here, but the electrons and the protons are essentially forced together and the atoms collapse in structure. Now, an atom, the stuff that we're made of, is actually about 99+% empty space. You've got the core of the nucleus with the electrons going around, but the actual atom is mostly made of empty space. So as the electrons and the protons get smushed together, all that empty space is essentially squeezed out, and all that material gets crushed down into a ball that is just neutrons. And those neutrons get packed together again as tightly as they possibly can be. You run into a second boundary called the neutron degeneracy limit. And that can push back with a much stronger force. So if your core isn't too massive, that neutron degeneracy can be enough to stop the collapse of the neutron star. And what you end up with is a neutron star at the end of the collapse. And that transition from the collapsing star to that rigid neutron degenerate material produces a shock wave that then pushes back outwards through the star and is what triggers the supernova explosion. If your star is just a bit too much on the heavy side. So if it's heavier than about 20 times the mass of our sun, even the neutron degeneracy force isn't enough to stop the collapse. So the whole thing just falls down into a black hole.
That's super interesting. I've never heard of I'm sure many of our viewers have not heard of electron degeneracy or neutron degeneracy, and it's really fascinating to hear all of this stuff from you, Andrew. Just another really quick question. Will our sun, at the end of its life, form a neutron star, or will it form something else?
So our sun isn't quite heavy enough. Our sun weighs 1 solar mass. Normally, to get to the core collapse supernova process where you get either a neutron star or a black hole, you have to have a sun that is at least 8 times the mass of what our sun is. The reason for that is because you need to be able to get to those heavier and heavier elements. And to get that, you need a more massive star to create the interior conditions that can fuse those heavier elements. What our sun will eventually do in some 4 to 5 billion years' time. So right now, our sun is in the process of fusing hydrogen, which is what most stars are almost entirely made of, into helium. So hydrogen is the lightest element in the universe. It's what most of the universe is consisting of. Helium's the next element up that periodic table in weight. Now, I'm not an expert on what our sun's eventually going to do, whether the helium will be enough to start fusing into heavier elements, or whether it's going to stop at that helium core stage. But eventually, the sun will not be able to produce fusion at those heavier elements anymore. It won't be able to get to the point where it gets to iron. It will stop too soon. When that happens, the star will have eventually expanded and shed its outer layers. What you'll be left with at the end of that process is what's called a white dwarf. And that white dwarf may be consisting of mostly helium, or it might have some slightly heavier elements like oxygen or magnesium, but it won't be able to get to a supernova stage. Unfortunately, it's not heavy enough.
Thanks so much, Andrew. It's really fascinating to hear what are pulsars, what are neutron stars, what the fate of our sun is, all of that within just the span of 5 to 6 minutes. It's really fascinating to see where this podcast interview will go. If you would like to start taking your own photos of the night sky, then make sure to check out this podcast series here. Make sure to subscribe, like, share, and comment down below. Trust me, I'll respond. Test me.